Hello everyone, this time we're working through example 9-19. Oop. Seriously, every single time. 9-19 in your textbook. Okay, what it says, it's a long problem statement. I'll read it out and then start doing the problem. It's a copper wire 150 feet long and an 1/8 inch in diameter is suspended vertically from its upper end. The unit weight of the copper is 550 pounds per cubic foot. Compute the total elongation of the wire due to its own weight, the average strain due to its own weight, the total elongation of the wire, which includes the elongation due to its own weight, if a weight of 70 pounds is attached to its lower end, and the maximum load P that the wire can safely support at its lower end if the allowable tensile stress is 12,000 psi. Okay, a lot going on there, but we have a wire that's 150 feet long, which is suspended from the ceiling. 150 feet. And it says it's an 1/8 inch in diameter, not very big. We also get a unit weight. So weight per volume is equal to 550 pounds. My pen is giving out again. There we go. Pounds per foot cubed. Okay. Now let's stop there because weight per volume isn't as helpful as just plain old weight. So let's figure out the volume of this wire. So the volume of the wire would be equal to its area, since it's circular, it's going to be a circle, which would be pi over 4 d squared times its length. This is the area of a cylinder, so the volume of a cylinder. Now, my diameter is given in inches. My length is given in feet, and my volume right here, the weight per volume is given in feet cubed. So I need to switch my inches to feet in this case. So the volume is going to be pi over 4 times 0.125 divided by 12. That's changing it from inches to feet. Feet squared times 150 feet. Okay. And this value right here is, let's plug it into the old calculator and see what we get. And we get a volume that is 0.01278. 0.01278 feet cubed. A small amount, but still appreciable. Now, if we then multiply that by 550, we get that the weight of the wire is 7.03 pounds. So the weight is equal to the weight over volume times the volume is equal to 550 times 0.01278. And it comes out to be 7.03 pounds. Okay, 7.03 pounds. Now, it asks us, what is the total elongation of the wire due to just its own weight? Just its own weight. Well, let's figure that out. Now, we know what the weight of the wire is. And that is going to be 7.03 pounds. So 7.03 pounds. Now, here is an issue. When we're talking about weight, we have to remember that that weight is starting at the top and it gets bigger as we go to the bottom. So the top of my wire is stretched a whole lot more than the bottom of my wire. Okay? Top of my wire is stretched a whole lot more than the bottom of my wire. Now we can still work with this. Just all we have to remember is that we're going to say that only half the weight is actually acting on the bottom. If you're wondering why that is, it's for a very, very interesting reason here. It's simply because that is going to be the combined effect. It's going to have a combined effect half as much as it would be normally when it comes to elongation, because this is the area of a triangle, and that's always 1/2 base times height. So that's where we're getting our load is going to be half. Okay, so plugging in this equation right here, I have delta equals P over 2, because it's only half the load is going to be affecting it, times length over AE. And I plug this in, and what I get is 7.03 pounds over 2 times 150 feet times 12 inches per foot, all over the area, which we calculated as 0.0123 inches squared. And then finally, modulus elasticity, which is going to be 15 million psi, because it's a copper wire. We can look that up. So 15 million. And that's going to be equal to, in the end, 0.0343 inches. Okay, and then the average strain is pretty easy to calculate because we already know what it is. We know the elongation, and we know the total length. We can use that. So our strain equation is the following. It's always equal to strain is equal to elongation over length. We know both of those. We can solve it. It's equal to 0.0343 inches over 150 feet times 12 inches per foot. And that's going to be equal to very, very small, 0.000019 inches. Oh, sorry, inch per inch. This is just due to its own weight, though. Now we can also find the additional elongation. We can just add these together due to an extra weight added on the end of the wire. So that additional weight, or additional elongation, would be delta equals PL over AE. But in this case, the load is going to be 70 pounds. 70 pounds because we're adding that on the end of the wire. So it'll be 70 pounds times the length, which will be 150 feet, times 12 inches per foot, all over the modulus elasticity, which is 15 million psi, times the area of 0.0123 inches squared. We plug that in and we get 0.683 inches. And so our total elongation is going to be equal to that plus our original elongation from just the weight. So it's going to be equal to 0.683 inches plus 0.0343 is going to be equal to 0.717 inches. Okay, now it's time to calculate stresses. So first let's calculate the stress due to just its weight. Stress is equal to load over area. This time we don't have to worry about like some sort of like integral equation. All we need to worry about is where is it going to be the worst. It's going to be the worst at the very bottom of the wire, where after it felt the full load, and that full load is going to be pulling on the very, very top of the, sorry, I said the very bottom of the wire. The very top of the wire is going to feel the full load of the weight beneath it and the weight. So that's the worst point. So the stress due to just the weight of the wire is going to be equal to its weight, 0.03 pounds, over the area, which is 0.0123 inches squared. It's going to be equal to 572 psi. Now we said that our allowable stress allowable, was equal to 12,000 psi. And we're going to try to calculate some max load from that. But before we can do that, we need to subtract off the stress that's due to just its weight. And so this gives us a true allowable stress of 11,430 psi. And then from that, we can finally calculate what our allowable load is. So stress equals load over area. I want to solve for the load, so I get that the load is equal to the stress times the area. And I get it's 11,430 psi. And that's multiplied by the area of 0.0123 inches squared to get a load of 140.6 pounds, which makes sense considering it's copper wire. Okay, now one thing I do want to hit on a little bit more is why in the world was this 1/2 for the load right here? Right here, this original elongation to the weight, why was that 1/2? And the easiest way to put it is to show it to you as sort of like an integral equation. So I'm going to move over here. I'm going to redraw my wire. And I have this wire right here. And what we realize is that if we look at it at the very bottom of the wire, then we felt the full load. At the very top of the wire, we felt nothing. Okay? Bottom of the wire, full load, top of the wire, nothing. And so it's increasing as we go. As we get longer and longer, the wire is feeling more and more of the load. But at the top, it feels nothing. It's not stretching. Well, I'm sorry, at the bottom, it's feeling nothing. It's not stretching. At the top, it is feeling everything. It's kind of weird how to put it there, but the weight is increasing as we go down the length. So we can actually get, sorry, this is a little bit wonky here. I'm trying to get it back over here. If we actually had wanted to, we could have calculated the weight per unit length. And we didn't do that. I'm not going to take too much time to try to do it right now. But we could have done that. But all we're going to know is that at the end, we're going to have a weight of 7.03 pounds. So we have our equation. It's delta equals PL over AE. And what you don't realize is that this is actually an integral equation. So the integral of d delta is equal to the integral from 0 to L of P over AE dl. Now most times this is constant. This is calculus here, you don't actually have to know this, but this is constant. And so when it's constant, it just goes back to our original equation. But P isn't constant. It's actually changing as we go. And it's changing as a function of L. It's per unit length. And so from that, instead of having to do this whole area right here, instead of doing an integral, what I realized is that P is going to be the area of this curve. That's what an integral is. It's an area of a curve. And so what I get is that delta is the area of that curve, which is just a triangle, which is going to be equal to P over 2 times L. 1/2 base times height. And then over AE because that's still there. So that is where that came from. That's a little bit higher level here. But you can just remember this, that if you have some wire under its own weight, you divide the weight by 2. Okay? Divide the weight by 2. Another way to think about that is that the weight always acts at the centroid, and that's halfway up, and so only half the weight's there. That's kind of a weird way of doing it. You can think about it as length over 2. So sorry, a better way of determining that would have been that the weight always acts halfway up, so you could have said that delta is equal to the weight, the full weight, times the length over 2, because that's where it's acting, over area times E. And you can see that those are equivalent. So that's probably an easier way of describing it. You put the weight at the centroid, that's halfway down the wire, and so you only have half the length in your equation. Okay, I hope that helped you, and I look forward to seeing you next and the last example for this problem, or for this chapter.